This is Richard Walker from Lucidate. Welcome to the fourth video in this series on cryptocurrencies. In this video, we're going to focus on what the architect of Bitcoin referred to as a timestamp server and proof of work to solve the double spend problem. This will introduce us to blockchain and the architecture and plumbing of cryptocurrencies. In the next couple of videos, we'll look at security issues as well as practical optimizations to enable cryptocurrencies to scale. This will include Merkle trees that lend scale to the hashing algorithm. In this video, we'll see how blockchain helps us to do three things. No double spend of Bitcoin, no altering or tampering of confirmed transactions, and to synchronize multiple copies of the ledger. Blockchain is the technology people most closely associate with cryptocurrencies and consequently what many people are most interested in. Partly this is because people have figured out that blockchain has many uses beyond crypto. In this video we will stay tight to cryptocurrencies but keep an open mind about where this technology might find a useful home in your business. When objects like files and messages are stored digitally, they're easy to duplicate. This is one of the key benefits of digitization. It allows us to very simply send emails, copies of spreadsheets, or derivatives confirmations from one place to another. However, effortless, costless duplication is far from a desirable trait in a currency. A monetary system that allowed anyone to duplicate their money at will would collapse instantly. Thus, the double spend problem. How can a receiver of digital money ensure that the money that they received had not been previously spent elsewhere? With paper money and metal coins, this is not really a problem. While a small amount of forgery is inevitable, the security printers of the world employ sophisticated systems to thwart many counterfeiters. Digital money has existed for over 6 decades. Transfer of digital funds across telecommunications networks is commonplace. The approach to counter double spend for such transfers has been to use trust and trusted intermediaries. Payment networks like SWIFT have evolved since 1973. Banks, central banks, clearing houses and mints are trusted to maintain their own private centralized ledgers to verify transactions. In the retail space, we have MasterCard, Visa, PayPal. Firms like Amazon and eBay also provide trust services. These are useful, effective constructs, but they are not without cost. An alternative is to use a public shared ledger with no intermediaries. This ledger maintains a complete history of all transactions. All transaction data is public and visible. To bring this about, we need to do a few things. Firstly, we need to make sure that no duplicated transactions can make it onto the ledger. In crypto speak, we need to ensure that a UTXO can only be consumed once. After being consumed, it's transformed into outputs, which are then the newly created UTXOs. Secondly, we need to make sure that the ledger is tamper-proof, that no one can go and alter the public ledger of confirmed transactions. Finally, we need a consensus mechanism. There's no master copy of the ledger held by a single trusted authority. Everyone has their own separate copy on which all the transactions are recorded. How do we make sure that this is synchronized and that everyone is looking at the same UTXO set? So what are the key components of Satoshi's trustless system and how do they interact? To help answer these questions, let's familiarize ourselves with some terminology and provide definitions. As with any large-scale system, there are several subsystems that have their own distinct role to play. The mempool or memory pool. This is a holding area or waiting room where prospective transactions are submitted prior to being included on the ledger. At this stage, these are unconfirmed and unsettled transactions. Accordingly, the mempool might include prospective fraudulent transactions. Nodes, a computer running the Bitcoin system. These nodes are part of a peer network. They connect and share blocks of transactions with one another. When a node first launches, it will download the entire ledger since inception, along with a database of all the UTXOs. Nodes can go offline, and when they return, they'll connect to a handful of peer nodes. They'll only need then to receive updates of the transaction history in the latest UTXO database from peer nodes from the time that they were offline. If a mempool is a waiting room, then a node might be thought of as a traffic cop, enforcing the rules of the Bitcoin protocol, validating transactions and blocks, making sure that malicious users can't commit fraudulent transactions. Miners. The aforementioned nodes keep track of the history of blocks and enforce the rules of the network. But where do the new blocks come from? The new blocks are created by miners. Miners take a bunch of unconfirmed transactions from the mempool. They check for double spending and will reject transactions that have invalid UTXOs as inputs. They place validated transactions along with some header information in a candidate block. A block is created when a miner solves a difficult puzzle by guessing a number. Much more on this arduous guessing game in a couple of minutes. For solving this near impossible puzzle, the miner is rewarded with Bitcoin. This is called the block reward. This incentivizes the miner to solve the difficult puzzle. Mining is the way by which new Bitcoin are minted. Blockchain, a database which groups transactions into blocks. Each block, other than the initial or genesis block, links to the preceding block. Think of the blockchain as a bound ledger to which you can only add pages at the end and can't alter existing pages. Each page of the ledger records confirmed transactions. As the ledger is bound, you can't alter the order of the pages, remove pages, or add pages in the middle. Wallet. Wallets generate and store a user's keys. Private keys are used to send payments. Public keys are used to receive payments. Wallets allow users to query their transaction history. This history allows them to determine their current holdings. Unlike a physical wallet, crypto wallets don't actually hold the currency. The money sits in signed, verified transactions on the ledger, but the wallet does hold your keys and has some nifty software to interact with the ledger to allow you to spend and receive Bitcoin, as well as see how many Bitcoin you have in total. So, these are the components. Let's remind ourselves of the requirements again. 1. No double spend. 2. No altering or tampering of confirmed transactions. 3. Synchronize multiple copies of the ledger. The solution proposed by Satoshi is to combine the new valid transactions into a block and to solve a difficult computational puzzle. Solving this puzzle is called proof of work. This proof of work must depend on the content of the new transactions and all prior transactions, as well as take a lot of computing time to solve. But the proof of work must also be trivial and instantaneous to check once the answer is known. If something is difficult, if it takes a long time and a lot of resources, then it's something you won't want to redo. So making the proof of work depend on the transactions and making it difficult defends against altering existing confirmed transactions. If a fraudster wants to alter the ledger and change transaction details, then they will need to find a new proof of work. To illustrate this, let's see how it works in practice. For this, we turn to our good friend SHA-256 again. We bundle our valid transactions into a block. This creates a text message. Any message will have a unique SHA-256 hash. Satoshi's suggested cryptographic puzzle requires us to add a single 4-byte integer number to this bundle of transactions. This single number is a number used once, or nonce. When we run the block of all valid transactions and the nonce through the SHA-256 algorithm, we will get a digest. The proof of work is to find a nonce that when we run SHA-256 on the valid transactions and nonce together, we will get a digest that starts with a fixed number of zeros. Let's say 50 zeros. This will require guessing and checking multiple times, trying out a whole range of guessed nonce values until we get a digest that starts with 50 zeros. Once a miner finds this nonce, then the block and the nonce can be broadcast to the whole network. It's trivial and instantaneous for nodes to verify that this nonce does indeed produce a hash with at least 50 leading zeros. But wait, I said this puzzle had to be dependent on all the new transactions as well as all of the prior transactions. How do we include all of those? The solution to this is simple and elegant. Rather than run SHA-256 on only 1, the new transactions, and 2, the nonce, instead run it on 1, the new transactions, 2, the nonce, and 3, the hash of the previous confirmed block. This gives us a chain of validated blocks. The proof of work on each block is a function not only of the content of that block, but because it includes the hash of the previous block, it depends on every block that preceded it. If a fraudster sought to alter the ledger in any way, then they would have to redo the proof of work in that block and every block that followed. One interesting case that can, does, and will happen, albeit very rarely, is when two miners mine a block at more or less the same time. Thus, both new blocks are broadcast to the network simultaneously. Some blocks and miners will receive block A before block B. Naturally, some will get block B first. What to do then? The simple answer is just to wait. The Bitcoin protocol says that miners must mine on the longest chain. That is the chain with the most proof of work. Miners accepting A will mine on that block. Miners accepting B will mine on that. One group will produce a result first. That will then be the longest chain, and all mining will continue on that. If by some freakish coincidence there's a tie again and a block mined simultaneously on both chains, then this process will continue until there is a longest chain. So while just wait seems to be too simple to be the correct answer, it is exactly what the protocol demands. This simple solution is what guarantees consensus and synchronizes the blockchains among all the peer nodes. Blocks that are minted on the shorter chain are orphaned. An orphaned block is a rare occurrence. At the time of video production, the last orphaned block occurred at 21 minutes past 3 in the afternoon on the 26th of August 2019. You can see orphan blocks at sites like bitcoinchain.com. If a transaction was in an orphan block, then there's about a 95% chance that it was also in the longest chain. If it was one of the unlucky 5% not in the longest chain, it will go back to the mempool to be picked up by another miner. Thus, the term blockchain neatly sums up how we accomplish our three requirements. Let's see how blockchain delivers the proof-based, trustless system that we speak. No double spend, no altering or tampering of confirmed transactions, and synchronizing multiple copies of the ledger. By only admitting transactions with valid UTXOs that are correctly signed into confirmed blocks, we guard against double spend. By requiring proof of work against current and all prior transactions, we can stop tampering and alterations. And by implementing the longest chain rule, we can ensure that the ledger is synchronized amongst nodes. So to summarize the workflow process, a payer's wallet constructs a transaction message based on the payer's UTXOs and the payee's address. The transaction message is broadcast to the network. Nodes pick up the message and perform validation checks. If the message passes all of these checks, a valid signature, valid UTXOs, etc., it's placed into the mempool. Miners pick up validated transactions, form a block, and attempt to find a matching nonce. The successful miner broadcasts the block to the network. Nodes check that the block is valid, and then a valid block is added to the chain. This is Richard Walker. Thanks for watching this video where we've described the key components of the Bitcoin system and seen how they operate together to validate transactions, solve the double spend problem, and generate distributed consensus independent of a central trust authority. In the next video, we will take a closer look at the anatomy of a block and look at how blockchain defends itself against certain types of malicious attack, including 51% attacks, Finney attacks, and race attacks.